The average rate of change of a function over an interval is the slope of a secant line that joins the two endpoints of the interval. In this example, we have the x squared function on the interval from 1/2 to 2, and the points a and b are showing x equals 1/2 and b is at x equals 2. So the red line is the secant line. We calculate the slope of the secant line using delta y over delta x. We can use f of x notation for that, as shown here. And the slope of the secant line is 2.5. Therefore, the average rate of change of the x squared function on this interval is 2.5. The instantaneous rate of change of a function at a particular point is the slope of the tangent line drawn at that point. In this image, we see the green line is the tangent line, and we are interested in determining the slope of the tangent line. Unfortunately, we don't have a way of directly calculating the slope of the tangent line, and so we look for a method which we can use to find that slope. The method starts by drawing a secant line connecting the point P that we're interested in to another point on the curve called Q. In this case, we have Q 1 unit to the right of P, as shown here by the delta x value being positive 1. When we calculate the y values for these 2 points and then use them together with the x values to calculate the slope, we get 3. 3 is not the slope of the tangent line, but it's our first approximation to the slope of the tangent line. Our second approximation to the slope of the tangent line is achieved by moving the point Q closer to the point P along the curve. This time we have an interval width which is reduced to 1/10 or 0.1. And our revised and better and more accurate estimate for the slope of the tangent line is now 2.1. A further improvement is achieved by moving Q much closer to the point P. Here we have an interval width of 0.01 or 1/100th, and our revised estimate for the slope of the tangent line is 2.01. We repeat the process by putting Q on the other side of P. In this case, Q is at the origin at x equals 0. And that gives us a delta x value of -1, because Q is on the left-hand side of P. When we calculate the slope of this secant line, we get 1. We move Q along the curve towards P, and our revised slope is now 1.9, a better estimate than the previous one. A further improvement is made as Q moves even closer to P. So you can see that the delta x value is now -1/100th, or -0.01, and our better estimate that results is 1.99. If we look at the 3 slopes that we achieved when Q was on the right-hand side of P, and we name them R1 and R2 and R3, that gives us a sequence of numbers, which are slopes. And the sequence is 3, and then 2.1, and then 2.01. Plotting those on a number line shows us that they're approaching some value. The value appears to be the number 2. When we look at the slopes of secant lines drawn to the left-hand side of P, we see another sequence of numbers, which are denoted L1, L2, L3 here. And when we plot those numbers on the number line, we see that they're moving to the right and also towards the number 2. Here are all of the slopes shown together on the number line. You can see that the slopes from the left are increasing and the slopes from the right are decreasing, and those two sequences of slopes are sandwiching in on some value. The value seems to be the number 2. We conclude that the instantaneous rate of change of the function at x equals 1 is 2, the slope of the tangent line.